Welcome back, everybody. I'll screen share. So I hope everyone can see this. Lecture 2. So yesterday we saw what the issue was with the counting functions for Diophantine equations or algebraic varieties, depending on your point of view. And we saw some of the behavioral phenomena for these counting functions. And I mentioned briefly some of the results that could be proved by the determinant method.
Sorry to interrupt, Roger. I don't know if
Yes.
you have advanced a slide, but we have not.
No, I haven't.
Okay.
We're still on slide 1, I hope.
Good. All right. Thank you.
Let's try this. This is slide 2.
Okay. Okay.
Good. That's working. Excellent. So what we're planning to do today is to, well, prove the theorem that I've brought up. This is going to be the basic theorem proved by the determinant method. By the p-adic determinant method, that is. So let's run through the statement of the theorem and make some comments about it. So we're going to have an absolutely irreducible form f with integer coefficients. It's going to have degree d. And we're going to give ourselves a small positive epsilon. And b, as before, is the parameter that measures the size of the box where we're counting solutions. And what the determinant method shows is that there is some large degree bound capital D that depends on the number of variables n, the degree of the original form f, and this small positive epsilon. And there's an integer k, which is bounded in this slightly complicated way. We'll come back and look at that bound in a moment, but there's a bound for the integer k that depends on the box size b. And there are forms f1 through to fk, again with integer coefficients in n variables. And these forms are co-prime to the original form f. And they have degree bounded by this integer capital D. That's to say they're bounded in terms of n, d, and epsilon. So we have these auxiliary forms. And they have the property that every x that we're interested in, all the x's counted by nbf, that's to say all the solutions of f equals 0 in the box of size b, are zeros of some other form fj. So you can envisage, maybe in the case of a surface, all the points on the surface that lie in this box are also points of one of the surfaces fj equals 0. So there are these auxiliary forms that cover all the points of relevance. And these auxiliary forms have bounded degree, and the issue then is just how many forms we need to cover all the points. And let me emphasize that this degree bound D is independent of the box size. So we don't really know how large it is, particularly in this theorem, but we do know that it's independent of B. Okay, so we'll look at the consequences of the theorem in a moment, but let me say that there are number field versions of this. There are versions that apply to affine varieties, to, let's say, polynomials rather than forms. There are versions that work for bihomogeneous forms, etc. Moreover, there are results that apply to general varieties and not just to hypersurfaces. And one way to prove such results would just be to project one's one's variety down to a hypersurface. And so, for example, if you had a curve in free space, then you could just project it onto a plane and count the points on the plane curve by using a result for, well, in that case, a plane curve. Yes. Okay, so we'll have to think about that in a moment, but let's see some more about what this theorem leads to by looking, first of all, at the case n equals 3. So in that case, the bound on the degree says that the integer k runs up to b to the 2 over d plus epsilon log f cubed. So this horrible exponent here, in the case when n is 3, that reduces to 2 times d to the minus 1. So that's the exponent that you see in this result here. So in particular, the number of auxiliary forms is fewer the larger the original degree d was. So you might need lots of auxiliary forms in a case when you start off with a quadric f, but for higher degree forms, you don't need as many auxiliary forms. Now, the points, therefore, that we're interested in not only satisfy fx equals 0, they satisfy fj equals 0 for some j. And so we have points that lie on the intersection of two curves. F equals 0 has degree little d, fj equals 0 has degree at most capital D, and so by Bezout's theorem, the intersection of these two has at most d times capital D points for each of the possible values of j. And recall that this capital D only depended on the number 3 and the degree d and the number epsilon, so it's bounded in terms of d and epsilon. So the number of points on each intersection is bounded in terms of d and epsilon. So the overall number of points on f equals 0 is bounded by the number of possibilities for j. So we deduce that the overall counting function is of order b to the 2 over d plus epsilon times log f cubed. And then we can go on to remove the f dependence by that final lemma that I proved last time. So in this instance, n equals 3, you start off with a projective curve in P2. The auxiliary forms say that your points of interest lie on the intersection of f with some other curve. You count the points on each intersection, finite number given by Bezout's theorem, and then you sum these up to the possible values of j. So that works very nicely. Let's see what happens with n equals 4. Now this time the number of auxiliary polynomials fj is b to the 3 over square root d plus epsilon. That's what that complicated expression in the exponent leads to. And now we have log f to the 5th power. And what happens now is that each auxiliary form produces points that lie on both f equals 0 and fj equals 0. So this time we have the intersection of two surfaces. So this is producing some sort of curve in 3 space. And again, the overall degree of this curve is bounded by at most d times capital D. So it's bounded independently of capital B. So the situation is rather more complicated this time. We start off with counting points on a surface, and we're reduced to counting points on a relatively small number of curves. So we would like to know how many points there are on each of these curves. Unfortunately, that's just what we've been talking about. We know how to do that. These curves, however, are not plane curves. They lie in P3. And so we could, for example, project them to P2 and use what we know about the n=3 case. Now, I need to emphasize that the theorem doesn't tell us anything about the size of the coefficients of fj, so we don't know anything about the height of the curve, just how complicated it is. All we know is that its degree is bounded. So it is important that any theorem that we use to count the points on each of these curves only depends on the degree and not on which curve we're talking about. So this is why uniformity with respect to the curve, a bound that only depends on the degree, is so important. So, for example, if you wanted to count the points on these curves using Falting's theorem, you would have a bound which is finite, but depends in some complicated way on the curve, and we don't have the information about what this curve is like. Now, if we have a curve of degree delta, well, the previous theorem tells us a number of points will be of order b to the 2/delta plus epsilon. And we have an upper bound for delta. It's at most d times capital D. The implied constant here will depend on epsilon, but also on delta. But fortunately, since delta is bounded in terms of the original d and n, this dependence here can be replaced by dependence on d and epsilon. So if the curve that we get here has degree delta, the number of points on it will be of order b to the 2/delta plus epsilon. Okay. Well, large values of delta are good and small values of delta are not. Let's just look back at that bound. The exponent is 2/delta. So if this delta is large, we get a very tight bound. And if this delta is small, if it's only 1, then this is rather a large bound. Now, sadly, we have a nice upper bound on delta, but we don't know how small delta might be. So this curve is not necessarily irreducible. It could break up into lots of curves of small degree. So what we want to know is what we can say about the possibility that delta might be small. And we know, for example, in the case of a cubic surface, that if it's got even one line on it, that will produce an awful lot of points. So small values of delta are a matter of concern for us. Now, it turns out that if you start off with a non-singular surface, there are a few curves of low degree. So here's a theorem due to Collier-Tollen, and it generalizes the statement that a non-singular cubic surface has, well, in this case, exactly 27 lines. So you might ask, well, how many lines does a non-singular quartic surface have? Does it have a bounded number of quadric curves in it, etc.? So here's the theorem. You have a non-singular surface in P3 of degree D. And then for curves of degree delta up to D minus 2, there's a constant independent of F such that the surface contains at most capital N irreducible curves of degree delta. So if D is 3, that means delta has to be less than or equal to 1. There's a constant independent of the surface such that every, in this instance, cubic surface contains a bounded number of curves of degree delta, of degree 1. But if this was a quartic surface, there will be a bounded number of lines and a bounded number of conics, degree 2 curves. And similarly for higher degrees. This does not happen if delta is equal to d minus 1, so a cubic surface contains infinitely many quadric curves. Similarly, a quartic surface can contain infinitely many cubic curves, but only a bounded number of low degree curves. So if the curve has degree delta bigger than d minus 2, well, then delta is at least d minus 1, and the number of points on that curve will be of order b to the 2 over d minus 1 plus epsilon by the theorem that we have for curves. And smaller degrees can occur in at most a finite number of cases. So let's put that together into this theorem, which may take a little bit of digesting. So we'll have a surface F defined by F equals 0, a non-singular surface in P3 of degree d. Then there's a fixed collection of curves, C1 to CK in the surface, with K bounded. So these will be the curves of degrees up to d minus 2. So in the case of a cubic surface, these will be the lines that lie on the surface. In the case of a non-singular quartic surface, will be the lines and the quadric curves. And then if we exclude these curves from the surface, so we look at S minus all these curves, and we count rational points P that are in S but not in any of these curves, with height at most B, well, they'll have to lie on curves of degree delta bigger than d minus 2. Each of those curves has at most b to the 2 over d minus 1 plus epsilon points. And the previous theorem told us that there are at most b to the 3 over root d such auxiliary curves to worry about. So we've got this fixed collection of curves that we have to remove, but once we've done that, the number of points left is like this, with an exponent here, whoops, that tends to 0 as d gets large. So for large degrees, almost all the points lie on the surface, lie on one of this small collection of curves, this fixed collection of curves. Now, an important conjecture in the study of surfaces, in the case of non-singular surfaces, is the Bombieri-Lang conjecture, which would say this, that if you have a non-singular surface in P3 of degree d at least 5, so this would be a surface of general type, then there is a fixed collection of curves, C1 to CK, such that all rational points on S lie on one of these curves. So the theorem we can prove says that apart from this rather small number, all the points lie on these curves. The Bombieri-Lang conjecture would say that all rational points lie on one of these curves. And there's a slight difference in that our collection of curves, the number of curves is bounded in terms of d alone. In the Bombieri-Lang conjecture, one only asserts that the number of curves you need is bounded in terms of F. So in one rather small sense, our theorem is actually more powerful in that it has this uniformity. And so for surfaces of high degree, we have this approximation to the Bombieri-Lang conjecture. So what happens in higher dimensions? So we've talked about curves and surfaces. Well, in effect, you would use theorem 1 repeatedly. So you would intersect your variety with one of these auxiliary varieties and get something of lower dimension, and then look at the number of points on that and use the theorem again inductively. And in general, what happens is that you need to study subvarieties of low degree, because those are the subvarieties, those are the places where you might get lots of points. So here's just one example that has been studied. The case of equal sums of 3 Deeth powers. So this is with positive xi's. And this is of interest in connection with Waring's problem, potentially. Now, there are trivial solutions in which x1 to x3 are a permutation of x4 to x6, so that gives b cubed solutions. And one would conjecture that there are a smaller order than b cubed number of non-trivial solutions as soon as d is at least 4. Indeed, I guess it's conjectured that if d is at least 7, one only has the trivial solutions. So this statement that almost all solutions are the trivial ones, that there are little o of b cubed non-trivial solutions, that was proved using the determinant method as soon as the degree is at least 33, and then sharpened to degree at least 26, which I think is the current record by Sahlberg. But there are other examples of higher dimensional varieties that have been tackled by the determinant method. Okay, so now it's time to think about how you would prove theorem 1. The first thing we do is to deal with the singular points on f equals 0. Well, singular points are defined by the vanishing of the partial derivatives. So all we need to do is to include each of these partial derivatives amongst the fj's. And of course, there are n of these, so that's bounded in terms of n and d. Now we're talking about the p-adic determinant method, so we're going to use an auxiliary prime p, and we're going to work p-adically. So what we actually need are points that are non-singular modulo p. So let's look at the sets S of b. These are the points on f equals 0 in the box x less than equal to b, for which grad f is non-zero. So these are the points that are non-singular. And we'll have the corresponding sets SBP, which are the points that are non-singular modulo p. And we know it's enough to consider only points in SB. We'd like to know it's enough to consider only points in SBP. So here's a lemma that allows us to do this. We take r to be the integer part of log is the height of the form f times b, and capital P bigger than log squared. Then we can find primes p1 up to pr, here's r, all of size order capital P, such that the set SB is the union of the sets SB, PI. And so in order to study SB, it's enough to study these sets here, and it's enough to prove a bound that relates to SBP for an individual P. Now I should emphasize that it's this lemma, it's the only place where the size of F comes into play. How do we prove this? Well, we choose a suitably large constant, depending only on d and n, choose it later specifically, and we just choose the primes pi to be the first few primes bigger than c times capital P. And because capital P is at least the square of r, these first r primes will all be of order capital P. Now let's suppose we had an x that wasn't in any of the sets S, B, Pi. And that means that all the primes Pi divide grad fx. And so their product does. Now this means either that grad f is equal to naught, in which case we're in the original set SB, the point was singular globally, or grad f is bigger than the product of all these primes. And the primes are all bigger than Cp, so we get at the very least c to the power r. On the other hand, we know that grad f has size at most the norm of the function f, and the x's are of size b, so we get a bound norm f times b to the d minus 1. We estimate that crudely. R here was the logarithm of fb, so this is at most e to the d minus 1 times r. We compare this bound, c to the r, with the upper bound, and we decide that if c is chosen large enough, this is enough to show that grad f is 0. So this lemma shows that if x is non-singular, it's non-singular mod one of these p's. Okay, so it's enough to examine SBP, the points that are non-singular mod p. Okay, now let's name the variety f equals naught. We'll call that v in projective n-1 space. And what we're going to do is think about the reduction of a point x modulo p. So we'll suppose it reduces to a point t in the FP version of the variety. And then for a given t, we'll let st be all the points that reduce to t modulo p. And in fact, since we're working in projective space, these x's will reduce to some multiple of t. So all the points that reduce projectively to t. And we can partition SBP up into the sets ST, where t runs over the non-singular points of V modulo P. And what we're going to do is examine the sets ST. And it will turn out, spoiler alert, that there will be one of these auxiliary forms fj for each value of t. The number of points t that we need is the number of fp points on V, that's order p to the n-2. So this will lead to the number of auxiliary forms that we're going to be having. So here's our goal. We're going to show that if little p is of order exactly p, with capital P suitably large, then each set ST is annihilated by a suitable form fj. And it will turn out that suitably large is this large. And because of the number of points on each, the number of the points on VFP, p to the n-2, that will mean that the number of, so I think this should say that the number of forms that we need is of order p to the n minus 2, which is going to be this big.
Roger, is that bound p to the n minus 2? Is that a Schwarz-Zippel type upper bound, or what?
Sorry, say that again.
Or I guess on the previous slide, the bound for in the last line of p to the n minus 2
So
for the number of points, that's Schwarz-Zippel, or is there any extra input?
This is the trivial bound that you get. We're working in projective space. We have one constraint, so we would expect exactly p to the n minus 2 solutions. So there, what am I trying to say? There are some tiny complications in proving that, nothing serious. It really is just a trivial bound.
Thank you.
And we don't need anything more. Sorry, that bit there should say the number of auxiliary curves required rather than the cardinality of SBP. So this is the bound for K that you saw in the theorem, modulo some minor further steps. And these log factors here involving F, they're only required to ensure that lemma 1 applies. We needed P to be at least of order log squared F in that lemma. Okay, it's time to have some polynomials and determinants. I should have emphasized, I did mention in the first theorem that the auxiliary forms Fj were co-prime to F. That's obviously important because if you are going to consider the intersection of the variety, or say the curve F equals 0 and the curve Fj equals 0, you want these to be distinct. So we're going to assume for simplicity, it's not really necessary, that capital F actually contains a term xn to the power d with non-zero coefficient. And we're going to choose our capital D, large in terms of d n epsilon, but independent of b and p. And we're going to consider the set curly E of monomials of degree d of this shape, in which this final exponent en is strictly less than d. And the reason we're doing that is that if g of x is constructed as a linear combination of these monomials, then it won't have a term xn to the d divisible by xn to the d. And so it's impossible for fx to divide gx. So this constraint here, along with this assumption, is a rather cat-handed way of ensuring that fx does not divide gx. And indeed, the fj that we produce will indeed be linear combinations of these monomials. We need to record for further use the fact that if capital E is the number of monomials we have, it is something like this quantity. It's easy enough as elementary combinatorics to get hold of this. Okay, so now let's write down all the vectors counted by S of t. And we'll list them as x1 to xn. They're vectors of size at most b that lie on f equals 0 and reduce projectively to the point t modulo p. And we write down this matrix M1. It's got capital N rows, each indexed by one of these vectors, xi, and capital E columns given by the various monomials. So it's an n by e matrix. And the big claim is that this has rank strictly less than E. So the columns we claim are linearly dependent. Now, if we can prove that, there will be a non-zero vector C such that M1C is equal to 0. It's a principle we saw yesterday. And this capital C can be constructed out of the various subdeterminants of M1. So this capital C will have entries CE, not all 0, with the property M1C is equal to 0, and that means that CE times the monomial xi to the e vanishes for each of these xi's. So that's the principle that we had last time, that this sort of vector equation involving a matrix of monomials times a coefficient vector, where the matrix has rows corresponding to the various solutions x1 to xn, produces a form, capital G, that vanishes at each of the xi's. And so this gives us the auxiliary form fj that we need. It will have degree exactly capital D, and by this little business of ensuring that there are no terms divisible by xn to the little d, these fj's are automatically co-primed to capital F, and they annihilate every vector that we're interested in. Okay, so we've got this matrix. We want to prove that its rank is strictly less than E. How do we do that? Well, this is obviously trivial if capital N is less than E, and otherwise it suffices to show that the rank is less than E for each E by E submatrix of M1. So we're going to look at the determinant of the E by E submatrices of M1. Well, might as well consider the submatrix produced by the first E rows. And we're going to show that the determinant of this is 0 if the auxiliary prime P is chosen suitably. And this is the determinant that gives the method its name. It's a determinant constructed out of monomials in various of the solutions f equals 0. So how are we going to prove that det M2 is equal to 0? Well, we're going to compare the Archimedean size with the p-adic size. So the fact that the x's have norm at most b, that means that these monomials have size at most b to the d. It's an E by E matrix here. So the determinant has a size at most E factorial times b to the de. So that's the Archimedean size. And so what we're going to do is show that the determinant of M2 is divisible by a very large power of P. P to the V with P to the V bigger than E factorial B to the DE. So that will be enough to show that det M2 is 0. So the name of the game now, from now on, is to examine the p-adic size of det M2. And so from now on, we can forget that the x's are integer vectors. It's enough to think about them as p-adic integers. So we've got to do a little bit of normalization. Remember that these xi's were in the set ST, so they're projectively congruent to a multiple of t, rho I times t, and these are supposed to be primitive vectors, so p will not divide rho I. And for simplicity, again, we'll assume that this vector t has first coordinate 1. And that means we're going to be allowed to assume that p does not divide the first entry of xi. And so we'll normalize xi by dividing by its first entry. So this is the vector xi, here is its first coordinate, and that will produce a vi that is congruent to t. So now if we take the matrix M2 and divide its ith row by this, that's to say the east power of this number, what we will get is a matrix containing not the monomials in xi, but the monomials in vi. And because we're dividing by something that is a p-adic unit, that won't affect the p-adic valuation. So it's a little bit of normalization to ensure that the first entry of these v's is always 1. Now remember that t was a non-singular point modulo p, and again we'll suppose for simplicity that the second partial derivative is not a multiple of p, and we can then use Hensel's lemma to produce a p-adic integer vector u congruent to t modulo p with f equal to 0 and with u1 equals 1. So we've now got a point that actually lies p-adically on f equals 0. The point v is p-adically close, or it's congruent modulo p to u. And so we can use the implicit function theorem over zp to solve the equation f1 of v2 to vn equal to 0. Writing v2 as a power series in the remaining variables for v in a suitable neighborhood of u. In particular, it's enough that v minus u has norm at most p inverse. So here's a formal statement of that in slightly different language. That there are power series in v3 to vn with integer coefficients such that if fv is equal to 0 with leading coefficient 1 and v congruent to u modulo p, then v2 is given by this power series. And this is in fact exactly the situation we've created for ourselves on the previous slide. vi is congruent to t, so vi is congruent to u mod p, and vi is equal to 1. So we're in exactly the situation for this lemma. The first coordinate of v is 1, the v is congruent to u. And that means we can think of the entries in this matrix M3 as power series in V3 to Vn. So we've got rid of 2 of the variables, in fact, by this process. And the fact that V2 is this power series is encoding the fact that our point lies on f equals 0. Now, because vi is congruent to u modulo p, it makes sense to write vi as u plus yi, where this yi is actually a multiple of p. So instead of thinking this as a power series in V3 to Vn, we make this substitution and think of the entries as power series in Y3 to Yn, which are multiples of P. So you can begin to see where the large powers of P that are going to divide the determinant are going to come from. So we have a power series in which the variables are all multiples of P. And now the general scheme is to perform elementary column operations on this determinant in order to eliminate low order terms from some of these power series Gj. So I need to explain what we mean by low order terms. So we're just going to choose an ordering on the exponent vectors. So remember, these were power series in Y3 to Yn, so we have exponents E3 through to En. We're going to choose the ordering in such a way that the exponent vector E is less than E dashed if the degree of Ej is smaller than the degree of E dashed. And when and I don't really care what happens if these have the same overall degree. And we are going to order monomials involving a coefficient, a non-zero coefficient, by saying that Cye is less than C dashed Y to E dashed if either one exponent is less than the other, or the two exponents are the same, but this has a larger p-adic valuation than that. So first of all, we see how the degrees of the terms compare, and if the degrees, if E is, and otherwise we see how the leading coefficients compare. So here's how we perform those column operations. We start by moving the power series with the smallest term to column 1. And the way we've set up this ordering means that this smallest term is then going to divide all other leading terms present. So we can subtract integer multiples of column 1 from all the other column terms to eliminate all other occurrences of Ye. So we might have to go back and think about how that ordering was defined in order to see that this is actually possible. Having done that, you move the column with the second smallest leading term to column 2, and you repeat the procedure. And so what you end up with is a matrix in which you have power series still with ZP coefficients, but each of them having a different leading term. But of course, the determinants are still the same. Now, because they're power series in Y to the E, the jth column is going to be divisible by P to the E3 plus P to the En, because each of the Yi's here is divisible by P. And now we can do a little calculation. The number of these monomials of degree f is given by this. So if j is bigger than a sum like that, you can work out that the jth column is divisible by p to the k plus 1. There's some slightly nasty calculations with binomial coefficients that I'm going to run through rather fast. So I don't suppose you'll follow all this straight away. But you can then see that having rearranged the columns in this matrix, the various columns get divisible by larger and larger powers of p. And then we have a condition that depends on capital E. That was the number of columns in the original matrix. And overall, given that we know that each column is divisible by a certain power of p, p to the v divides the determinant with an expression for v like this. And then if we work out the comparison with the power of p dividing det m4 with its Archimedean size, we find that det m4 has to be 0 if p is large enough. Okay, so we produced a large power of p dividing the determinant. That will show that det m4 has to be 0, providing p is this large. So going back to the previous slide, we had a constraint here involving log e factorial. There's an e here. There's the v that we've got this horrible formula for, another v here. D and n are fixed. This factor here is relatively harmless, so we have to choose capital D to minimize this part of the formula, and that means choosing capital D very large. So the message here is that when you do this process, the degrees of the monomials that you use are rather large. So here's the asymptotic analysis of how the E looks. This is actually the size of E that you need in terms of this parameter K. Let's skip through this. And when you do all this, you find that the key quantity involves this expression here, which is the one that occurs in theorem 1. So ultimately what we find is that if you chose your degree D large enough in terms of the other parameters, det m4 will be 0 when p is this large. And that completes the proof. So perhaps the take-home messages are, first of all, you construct a large matrix involving monomials with one row for each of the solutions you're interested in. The solutions have been partitioned according to the FP point over which they lie. The fact that they all lie over the same FP point produces large powers of P in this determinant. You compare this large power of P with the Archimedean size of the determinant, and if your P is chosen suitably large, the determinant is 0. Okay, so that's that. Next time we're going to look at alternative versions of the determinant method, and in particular, the approximate determinant method.